Hello everyone and welcome back to the next lecture in Chapter 2, and this one's going to be about chemical bonds. Atoms link through chemical bonds. When two atoms do link up, they are less likely to react again, which just means that they are more stable. So when atoms link together, they're more stable than when they're just sitting out on their own. A bond, the definition of a bond, is a weak or strong electrical attraction that holds atoms in the same vicinity. So please note that atoms never directly touch. There's actually no force on Earth that is strong enough to put two atoms together to touch, because the electrical charges that they have, the proton positive charge and the electron negative charge, are so strong that you actually can't put them together. So think about trying to push two magnets together, and if you get really strong ones, it's very, very hard to get them to touch. Well, these are the strongest negative electromagnet things that we have, and there's literally no force on Earth that can put them together. A grouping of two or more atoms held together by chemical bonds is called a molecule. And so if you have two atoms of the same type, for instance in hydrogen, we have hydrogen gas is H2, or oxygen gas is O2. And so a grouping of two or more of those atoms is called a molecule. So a molecule of hydrogen gas or a molecule of oxygen gas is actually two atoms. And when a molecule is made up of two or more atoms of different elements, it's called a chemical compound. So like a unit of water, H2O, is a compound. It's got two atoms of hydrogen bound to one atom of oxygen. Or a single molecule of methane gas has four atoms of hydrogen bound to one atom of carbon. Okay, so if you remember from the lecture of chapter 2.1, an atom typically has the same number of positively charged protons and negatively charged electrons. When this is the case, that atom has an overall neutral charge. But when an atom participates in a chemical reaction that results in the donation or acceptance of electrons, the atom gains a charge, positive if it loses an electron, or negative if it gains an electron. An atom that has an electrical charge, whether positive or negative, is an ion. So if we look at potassium, which is denoted by the letter K, for instance, it's an important element in all body cells. Its atomic number is 19 with a mass number of 39. It has just one electron in its valence shell. And that characteristic makes it highly likely to participate in chemical reactions in which it donates one electron, because it's easier to donate one electron than to gain 7. As you can see here, it has 2 in its first valence shell. Remember, that's as many electrons as it can take in that first, a full 8 in the second, a full 8 in the third, and only 1 in its valence or outermost shell. So it's easier to donate that 1 electron than it is to get 7 electrons. So that loss of that electron will give potassium a positive charge, because the charge of its protons, which are positive, will outweigh the charge of its electrons. It'll have 7 protons. It will have more protons than it will have electrons. At that point, the potassium ion is written as K+. Up here, K+, and indicating that it has lost a single electron. It now has a positive charge, and a positively charged ion is known as a cation. And if you want a little trick to help you remember that cations are the positively charged ions, I like to tell myself that owning a cat is a positive thing. And there you go. I don't know if that'll work for you, but it seemed to work for me, just to differentiate that the positively charged ions are the cations. Okay. Now let's take a look at fluorine, denoted by the letter F. Its atomic number is 9, and it has 7 electrons in its valence shell. Thus, it is highly likely to bond with other atoms in such a way that fluorine accepts 1 electron, because it's easier to get 1 electron than it is to donate 7. When it does, its electrons will outnumber its protons by 1, and it'll have an overall negative charge. The ionized form of fluorine is called fluoride, and it's written as F-. A negatively charged ion is known as an anion. So that's A-N-I-O-N, anion. I don't really have a trick for you on that one, but if you remember that cation is positive because cats are positive, then you just have to remember that anions are negative. And so ions are the positively charged molecules, cations are the positive, ions are charged molecules, cations are positive, anions are negative. The opposite charges of cations, positive, and anions, negative, exert a moderately strong attraction, and that will keep the atoms in close proximity, which form an ionic bond. So an ionic bond is the first type of bond we'll talk about. It's an ongoing close association between ions of opposite charge. So if you ever look at table salt, the stuff that you use for food, its existence is due to ionic bonding. Sodium, Na, usually donates an electron to chlorine. It's very easy for that to do that because sodium has 1 valence electron and chlorine has 7 valence electrons. It becomes the cation Na+, and when chlorine accepts the electron, it becomes the chloride ion Cl-. With their opposing charges, those two ions strongly attract each other, and they become NaCl, or table salt. So when you have a complete donation of electrons, that is called an ionic bond. Unlike ionic bonds, which are formed by the attraction between a cation's positive charge and an anion's negative charge, molecules are formed also by covalent bonds. Covalent bonds happen when two molecules share electrons in a mutually stabilizing relationship. So this figure right here shows several common types of covalent bonds. Notice that the two covalently bonded atoms typically share just 1 or 2 electron pairs. So up on top, this is a single covalent bond where they share 1 pair of electrons. And you see that when 2 hydrogen atoms will bond together. Here is a double covalent bond, and that happens when 2 oxygen atoms bond together. This is what a molecule of oxygen gas looks like. So here are the 2 pairs that they are sharing. So instead of having charges and becoming anions, these are still just regular molecules that share to become stable. And here is a carbon dioxide molecule, CO2, where carbon double shares with 2 pairs of electrons here with this oxygen and with this oxygen. So it's a 2 double covalent bonds. So this is pretty interesting about carbon. Carbon has 4 electrons in its valence shell. Thus, gaining 4 would make it more stable. So if it takes 2 from this oxygen and 2 from this oxygen, it becomes more stable. Oxygen only needs 2 to become stable, so this entire molecule is stable. Carbon having 4 valence electrons allows it to make a number of bonds that are very important for the existence of life on this planet. You might hear people describe the life on this planet as carbon-based life. And the reason for that is carbon has a really interesting number of valence electrons in 4, in which it can share electrons or donate electrons pretty easily. So let's look at this slide now. If you listen to a presidential debate, you might hear it described as very polarizing, or it's very polarized. And in chemistry, a polar molecule is a molecule that contains regions that have opposite electrical charges. Polar molecules occur when atoms share electrons unequally in polar covalent bonds. So it's still a covalent bond because they are sharing, but they're not sharing equally. It's like if I borrow your car for 3 days and then I give you your car for a day, that's, yeah, I guess we're sharing it, but we're not sharing it very equally. The most familiar example that I can give you of a polar molecule is water. This molecule has 3 parts. The oxygen atom, so the atom of oxygen, which has a nucleus that has 8 protons, and 2 hydrogen atoms whose nuclei only contain 1 proton. Because every proton will exert an identical positive charge, a nucleus that contains 8 protons has a much higher charge than a nucleus that contains 1 proton. So that'll mean that the negatively charged electrons that are present in the water molecule are going to be more strongly attracted to the oxygen nucleus rather than the hydrogen. So each hydrogen's atom, each hydrogen atom's single negative electron will then go more towards the oxygen atom, making the oxygen end of their bond slightly more negative than the hydrogen end of their bond. And this actually happens with the entire molecule. So not just in the bond itself, but in the entire molecule itself as well. And what you'll see is that if you look at the 3-dimensional model of a water molecule, you'll see that The hydrogen side of the molecule, so it's H12O, this is a slightly positive side of the molecule, and this is a slightly negative side of the molecule. When we see these regions, we call these partial charges because the strength of the charge is less than one full electron that might occur in an ionic bond. And when we also, what we call these are, we call them dipoles, so two poles. And that sort of makes sense. It's like a magnet that has two poles. But this allows water to do some really important interactions, and we call those hydrogen bonds. Hydrogen bonds are formed when a weakly positive hydrogen atom already bonded to one electronegative atom, for example, the oxygen in the water molecule, is attracted to another electronegative atom from another molecule. So in other words, the hydrogen bonds always include hydrogen that is already part of a polar molecule. So take a look at this. This is the covalent bond, right? This is the polar covalent bond between the oxygen and the hydrogen. The hydrogen bond is not an actual bond, it's more of an interaction between a hydrogen that now is slightly positively charged interacting with something that's slightly negatively charged. This case just happens to be another water molecule. And this gives water its properties. If you've ever seen two raindrops come together on a window and form into a bigger raindrop, or you've seen water take the shape of the flask or the cup that it's in, you've seen hydrogen bonding at work. So the way that our blood can flow through our body is due to hydrogen bonding, so that water molecules can really stick together, and it gives water this really important properties. Like if you've ever seen water flowing through a river, right? So all these things that water does are because of hydrogen bonding. And I just want to point out again, it's not an actual bond, it's more of an interaction, whereas these are the covalent bonds holding the H2O molecule together, but they produce this slightly negative, slightly positive dipole that then creates this hydrogen bonding interaction. Water molecules also strongly attract other types of charged molecules as well as ions. That'll explain why if you ever have poured salt or sugar, let's talk about salt for this example, into a cup of water, it'll dissolve because the NaCl, the ionic bond, the charged ions that make up the molecule of NaCl easily dissociate into the water. So the sodium, like I said, is positively charged, and the negatively charged chloride dissolves because it forms dipole ion bonds between the water and the electrically charged ions, and these are electrolytes basically. Water molecules also repel molecules that have non-polar covalent bonds. You've seen this before. If you've ever put any oils or fats or lipids into water, you know that they put some vegetable oil in some water, it'll bead up on the surface, and that's because the non-polarness of that molecule does not interact well with the polarness of the water molecule. And so that's all I want to say about bonding, and look forward to the next chapter coming up very soon.